at this point, I want to talk about area and how we find area and how that relates to distances. Now, if you recall from, say, geometry class, you learned how to find the area of things like rectangles, where the area is just length times width. And you learned how to find the area of triangles, where the area is one half the base of the height. You were able to take other objects, say, um, like a polygon. All right, how about that? Just some random polygon and cut it into three triangles and find the area of the individual triangles and add them up. You were able to find the area of a parallelogram by cutting it into a couple of triangles and a rectangle, finding individual areas and adding them up. Now, that's just some of what you did in geometry. You found the area of numerous objects, numerous shapes when you took geometry, but what you have not learned how to do is find the area of something that perhaps is shaped like that. So we had a curve, and we'll define it with, just so we can reference it, we'll say that curve is a right half of a parabola. We're going to go out as far as 1 on the x-axis, making that ordered pair 1, 1. And the area we're concerned with is the area housed inside that curve. We'll call it S, and just the portion of the curve from 0 to 1. Not going to worry about the left-hand side of the parabola. We'll just look at that. All right. The problem is that is not a square. That is not a rectangle. That is not a triangle. That is not a polygon, parallelogram, trapezoid, or any of the other objects that you've ever found the area of. Now, note that it is, if I was to draw sort of an imaginary horizontal line there, this region, this area we're looking for, is inside of this square, the square that is 1 unit tall and 1 unit wide. So we know the area of S is smaller than 1, since it is above the x-axis. Since it actually occupies physical space, we know that it's larger than 0, but that's not a lot of information. Okay, that's a pretty wide gap. All right. So how might we go about figuring out the area underneath the y equals x squared curve from 0 to 1? Well, there's a number of ways that we could attempt to do that. Let's sketch a few of them. All right, so first of all, what I could do, sort of in the spirit of what I did with this polygon, what I could do is come in here and chop this thing into pieces. I could start over here on the right hand side and I could say, all right, here, if I cut it like so and sort of figure in a straight line there, there's a little triangular piece. And I could come over here and cut it again and say, here's a little triangular piece. And I could come over here and cut one more time. Here's a little triangular piece. So you could take that curve and, in theory at least, chop it into little triangles like that. I will promise you, if you try and pursue that, you will find it to be difficult beyond measure. That is a extremely tough way to go. Triangles would fit that curve pretty nicely, but every single triangle is going to have a different base, a different height, a different this, a different that. That is just going to be an impossible route to go. Now, another option, and what we're going to do, whichever option we pursue, is try and make use of what we know about our standard high school geometry. Another thing you could do is you come in here and let's cut this thing into pieces. Let's cut the number line into pieces. Remember, that goes out to 1. So I'm going to chop this number line into, there's 1, 2, 3, and 4 pieces. That means since I'm only going out to 1 right here, that this is a 1/4. This is 2/4, also known as a half. This is 3/4, and here's your 1. All right. So I'm going to take this large object, this curve, this y equals x squared curve, and I'm going to cut it again into 1, 2, 3, 4 pieces. Now, technically, those pieces are of equal width. It's just the fact that I'm not a very good artist that makes them look unequal, so bear with me. And I don't want to do the triangle thing. You maybe, just maybe, in your future, have some triangle type cutting that might be done, but I don't want to do that. What I want to do is work with a shape that is much easier to calculate with. That triangle, that 1/2 base times height, that's not the easiest calculation in the world. An easier calculation would be to cut the curve into rectangles. Now, if you notice what I'm doing here, I'm using the right hand side of the interval to determine the height of the rectangle. All right, so I've got a rectangle that I'm going to use to approximate area there. I've got a rectangle I'm going to use here, rectangle I'm going to use here, and a rectangle I'm going to use there. All right, now remembering that the area of a rectangle is length times width, one reason why this is easier is because every single one of these rectangles is the same width. Any consistency like that that you can draw on is helpful. So the area, at least my area approximation, is going to be length times 1/4 wide for the first rectangle, plus length times 1/4 wide for the second rectangle, plus length times, whoops, I'm saying 1/4, writing 1/2, 1/4, 1/4, third rectangle, length times 1/4, and last rectangle, length times 1/4. There's my 1, 2, 3, 4 rectangles, all right? And by length, I'm talking about measuring in this dimension, and width is the 1/4 as measured in that direction. So how do I figure out each length? Well, again, the rectangles, their height, which I'm calling length, is measured using the right hand side of the rectangle as it touches the curve. So the right hand side of this rectangle touches the curve at an x value of 1/4. Therefore, the height will be the function value, which is 1/4 squared. This one touches at 1/2, which is 1/2 squared. This one touches at 3/4, which is 3/4 squared. This one touches at 1, which is 1 squared. Now, to make the calculations a little bit easier, it's really convenient to notice that 1/4 is a GCF here. So I can pull it out. And what I'm left with is 1/4 squared plus 1/2 squared plus 3/4 squared plus a 1 squared. All right? And that's obtainable. That's doable. All right? That area formula is easier to use. I'm going to put in a 1/4 times 1/4 squared plus 1/2 squared plus 3/4 squared plus 1 squared. Close parentheses, and that gives me a 0.46875. All right, so that is an approximation for the area underneath that curve. Now, how good of an approximation is it? Well, you can look at the sketch and it should be clear that it's an over approximation if nothing else, because there's area here that I counted which wasn't under the curve. There's area here that I counted which wasn't under the curve. Area here and area here. There's a lot of area, a considerable amount of area that I counted, that I measured, that's not actually under the curve. So this is an overestimate, right? How would we go about getting something the book doesn't mention as much? How to go about getting an underestimate? Well, an underestimate, and why would you want an underestimate if you've already got an overestimate? Well, because the true value is going to be somewhere between the two. All right, so same curve, ending in the same place. I'm going to cut it up into 1, 2, 3, and 4 pieces again. So these cuts would be at 1/4, 1/2, 3/4, and then it ends at 1. Okay. So what I did last time is I used the right-hand side of the interval. That gave me, in this case, rectangles that were overestimates. This time I'll use the left. So this is the area I will find. Using the left, this will be the area that I find. Using the left, this would be the area that I would find. And down here, if I use the left, since this thing hits the origin, that area is going to be at 0. All right. Again, just because it hit the origin. All right. So with that calculation, first of all, this rectangle, the one that got flattened out, is 1/4. Keep doing that. Not 1/2. 1/4 times the height, which was 0, plus this rectangle is 1/4 times the height, which was the 1/4 squared. Again, it's the left-hand side that's measuring the height this time instead of the right. Plus, once again, all right, first rectangle, the flat one is here. This rectangle is here. The next rectangle, 1/4 times the 1/2 squared, that's this rectangle, plus the 1/4 times the 3/4 squared. Once again, the 1/4 will factor out. And we've got a 0 squared plus a 1/4 squared plus a 1/2 squared plus a 3/4 squared. All right. And on the calculator, we'll go ahead and figure that. It's going to be 1/4 times a 0 squared plus a 0.25 squared plus a 0.5 squared plus a 0.75 squared, close the parentheses, and I get a 0.21875. All right, so what I therefore know is that the area, which we've denoted as S, is somewhere between a 0.21875 and a 0.46875. It's in there somewhere between those two. All right. Again, that's a pretty wide interval. Okay, that is a relatively wide interval. So how could I get this interval a little bit tighter? How could I get a better approximation? Well, I could repeat this process, and I'd actually have to go through it. At least it would be ideal to go through it 2 more times. All right, again, it ends at 1. This is the 0.11. This is the curve y equals x squared. How could I do a better job? How could I get a better approximation? Well, I'm going to cut it up again, but instead of 4 pieces, I'm going to cut it into 8. So I would cut it at 1/8, 2/8, which is 1/4, 3/8, 4/8, which is 1/2, 5/8, 6/8, which is 3/4, 7/8, and then 1. All right, and again, my artwork isn't the best, but Anyway, you get the idea. Cutting it into eighths, measuring the height of the rectangle on the right-hand side again would give me an overestimate again. All right, but the calculation can be done. Each rectangle will have a width of 1/8, so I'm just going to go ahead and pull that out, save us the time. And heights or lengths, if you want to call them, doesn't matter what name you call it by, measured on the right-hand side. So starting at 1/8, it'd be 1/8 squared plus 1/4 squared plus a 3/8 squared plus a 1/2 squared plus, and I'm not going to write all of these out since we're measuring on the right-hand side. The last one will be a 1 squared, and that will be, let me introduce some notation now. That will be the right-hand approximation, so we use a capital R to denote it. Right-hand approximation using 8 rectangles. That's what that would be if you were to finish that calculation. If we were instead to come to the left-hand side, this would be one of them. This would be another. Here's another. Here's another. The next one, the next one, the next one, and that one. The left-hand approximation using right-handed, 8 rectangles, left-hand side, would be a 1/8. Since we're working from the left-hand side, you would start with a 0 squared plus a 1/8 squared plus a 1/4 squared plus a 3/8 squared plus, and the very last one would not be the 1, it'd be the 7/8, again, because we're working from the left-hand side instead of the right-hand side. In the case of a function that increases, your right-hand rectangles are going to be your overestimate. In the case of an increasing function, your left-hand side is going to be an underestimate. That will change if the function decreases instead of increases. It'll change if the function goes up and down instead of steadily doing one or the other. Okay, so all these different shapes and behaviors of the function will change what's an overestimate and what's an underestimate. All right, and if you have a function that fluctuates up and down, even if you're doing a right hand, some of the rectangles will be over, others will be under, so that can just totally change at the whim of the function. So what we're seeing here is that the more rectangles that you use, hopefully there's a visual here that you're picking up on, and that is that the more rectangles you use, the smaller this over approximation or under approximation will become. All right, so use more rectangles, get more accuracy. All right, what would be, therefore, an ideal number of rectangles? So let's work this one more time to see if we can get not just a better number, but the best number. Once again, if you had y equals x squared out to an x value of 1 ending at the point 1, 1, how many rectangles should be used? Well, we saw that 4 wasn't as good as 8. 8 wouldn't be as good as 10. 20 would be better than 10. 100's better than 20. 1,000's better than 100. And where we're heading is that if we simply had infinitely many rectangles, then what that would give us is not an approximation, but an exact, to stress that, an exact area underneath the curve. So if we were able to do this with infinitely many rectangles, we would have an exact number. So here's what we're going to do. We're going to first set it up right-handed with some arbitrary number of rectangles. And that arbitrary number is n. All right? So if you take an interval that's 1 unit wide and divide it into n pieces, then each one of these rectangles will be 1 over n wide. So I'm going to go ahead and factor that out, not a half. I'm stuck on a half today. 1 over n. All right. The interval we're looking at starts at 0. The first rectangle is a distance of 1 over n to the right of that. So a 1 over n squared will be the first one. Step 1 over n further and you're at 2 over n. And we're squaring it because the function on the right-hand side is telling us how tall that rectangle is. Step over again. You're at 3 over n, and the height is 3 over n squared. Plus, and continue this until you get out to 1, which 1 is in the form of n over n squared. Again, 1 over n, 2 over n, 3 over n, 4 over n, 5 over n, until you get to n over n, which is the last one. All right. Now, from this, what I hope you notice is that in each of these fractions, you have a common denominator of n squared. So the numerator just turns into a 1 squared plus a 2 squared plus a 3 squared plus a 4 squared, all the way out to the very last one, which is a plus an n squared. So this n squared on the bottom, I'm going to throw it out front. All right, so what do I have here? I have a formula that I could use. If you, for example, say, well, I want to use an n of 10. Okay, plug in a 10, and you've got it. I want to use an n of 100. Okay, that's fine. Plug in 100, take this out, 100 terms, and you've got it. I want to plug in n of 1,000. Okay, fine. Plug in the 1,000, and it will give you the right-hand over approximation for 1,000 rectangles. But what was it we said was the ideal number? The ideal number is infinitely many rectangles, and that's where limits come in. If I take the limit as n approaches infinity of this right-hand approximation, I'm taking the limit as n approaches infinity of 1 over n cubed times 1 squared plus 2 squared plus 3 squared plus 4 squared plus all the way out to n squared. All right. Now the difficult part of this is right here. In pre-cal, you study a few sequences and series, all right? But the sum of those squares is not one you usually get to. So in the back of the book, there are some formulas provided. And the first, well, not the first, about the second or third formula you're given is the sum of squares like this. And that tells you that 1 squared plus 2 squared plus 3 squared plus 4 squared plus all the way out to some finite n squared is equal to n times n plus 1 times 2n plus 1 over 6. And if you wonder where that comes from, all you have to do is go look up some of the work of Carl Friedrich Gauss, and you'll see that he basically started a lot of this. All right, therefore, my r sub n formula becomes 1 over n cubed times this n times n plus 1 times 2n plus 1 over 6. Well, this n cancels one of those, and you've got a 6n squared on the bottom. I'm going to FOIL this out and get a 2n squared plus a 3n plus a 1. And then I will divide by the highest power, and the highest power is n squared. So it gives you a 2 plus 3 over n plus 1 over n squared over 6. And when I take the limit as n approaches infinity of that r sub n, which is 2 plus 3 over n plus 1 over n squared over 6, note that this turns to 0, this turns to 0, and 2/6 is a third. What that means is if I find the area of that region, if I approximate it using right-handed rectangles, and if I use infinitely many rectangles, that area comes out to be 1/3. What you would discover also, and it's an interesting exercise, but what you would also discover is if you did it with left-handed rectangles, you will get exactly the same result. All right, therefore, what we go on to do is define what we mean by area. Now, you may have thought that in geometry class, you defined area. You really didn't. You were given some area formulas. You did area calculations. You never truly, in the strictest sense, defined what area was. Well, area is defined as the limit as n approaches infinity of r sub n, which is equal to the limit as n approaches infinity of f of x sub 1, which is the x value on the right-hand side of the first rectangle, times what we call a delta x, plus f of x sub 2 times delta x plus, and this goes on and on until you get down to the right-hand side of the last rectangle times delta x. And you may be wondering, delta x, what is this delta x? Well, delta x is the width of each rectangle. Well, our rectangles were 1 over n, and that was because we used n rectangles for a region 1 unit wide. Well, for a region that runs from point A to point B, the width of each rectangle is going to be the right-hand end minus left-hand end. That's how wide the interval is, divided by the number of rectangles. So that's what we mean by delta x. And it is interesting, again, as I've already noted, to observe that if we define area using the left-hand version of the definition, it looks a little bit different. It's going to be f of x sub 0. F of x sub 0 meaning the actual literal left-hand end of the interval. Oh, that's a 1. A 1. And this one, instead of ending with f of x sub n, we end with f of x sub n minus 1. Okay. What you will find is that these two are equal. Right? These two limits always come out to be exactly the same. All right. So the definition, whether you use the left-hand version or the right-hand version, will turn out to be identical. All right. So we can find the area under a curve. So what? What does that help us do? Well, if you recall, let's see how this applies to the real world. If you recall, you've been told the distance equals rate times time. All right. What a lot of people don't realize about that formula is this only works if you're traveling at a constant rate. In other words, if you say that I'm going to travel for 3 hours at 60 miles per hour, how far will I go? Well, the distance would be equal to the 3 hours times the 60 miles per hour. Hours cancel. You're going to travel 180 miles. But this is only true if you travel 60 miles per hour the entire time. Okay? The problem is that's not the way it usually works. That's not the way it usually works. Let's say that at the moment you start your stopwatch, a car is already in motion and it's doing maybe 25 miles per hour. And here's what it does. All right. This is what your car is doing. Start out at 25 miles per hour. The moment you started your experiment at what would be called time zero. For some period of time, it sped up, it reached maximum speed, and then it slowed back down. Okay, can I just simplistically say, well, the distance that cars travel is equal to rate times time? No, you can't. There is no one rate. Rate fluctuated the entire time. You were never doing one speed for an extended period of time. Okay, but what you do note, what hopefully you do note, is that on this axis, I've got time. On this axis, I've got rate. So therefore, the area under this curve is the same as rate times time. So in other words, if you can find the area under this curve, you can find the distance traveled. In other words, if you were to cut this up and use these little rectangles, some right-handed, maybe others left-handed, the area under this curve will be your distance traveled. All right, so that is the first leap forward, is that area under curve can represent things other than just area. And again, in this case, when we have a motion curve like this, the area under the curve represents distance traveled. So you will be asked to find distances for something that is in motion, and you'll do it by calculating areas.